Let's wait for a couple of minutes.
Good evening, ma'am.
Good evening. Okay, let us start. I will share the slides now.
Yes, ma'am.
Is the slides visible?
Yes, ma'am, it is.
Okay. Good evening, all. Welcome to week 3 assignment of the NPTEL-PMRF tutorial of Introductory Organic Chemistry 2 by Professor Harina Chakrapani and Professor Neeraja Deshaputre. Myself, Anisha Suresh, PMRF TA for this course from IIT Bombay. So, here in this module, we will be discussing a brief summary regarding what was discussed in week 3 modules, followed by we will be solving some previous year assignment questions. So, coming towards the summary of week 3. So, in week 3, the basics of carbonyl compounds were discussed, where it involved the addition reactions on carbonyl functional groups and nucleophilic addition reactions and determining its stereochemistry. So, coming to basics of carbonyl compounds. So, how an addition reaction to a carbonyl compound is taking place? It involves two mechanistic steps. First is the nucleophilic attack on the carbonyl group, followed by protonation of the anion that will be resulting. So, we can see here in the case of here we are having acetone and it is treated with sodium cyanide in the presence of H2SO4 and water. So sodium cyanide here Cn minus will be acting as the nucleophile and this is the electrophilic sender, the carbonyl carbon. So the nucleophile will first add on to the carbonyl carbon followed by this shifting of electron. This bond will break and the electron will shift towards the oxygen. So we will be getting this tetrahedral complex. So it will be O minus. So it will undergo a protonation. So we are having an acidic medium H2SO4 and water is present. So there will be proton available in the medium. So it will undergo protonation which will further lead to formation of this product. So this product is known as cyanohydrin. Okay. So this is how a carbonyl compound will react towards a nucleophile. First, the addition of the nucleophile will take place on the carbonyl carbon, followed by protonation of the uh, anion, that is the O minus that will be formed. It will undergo protonation in the presence of the proton present in the medium, leading to formation of the final product. Now, coming towards the hybridization concept of this carbonyl compound. So we are considering formaldehyde here. So here you can see this is a C double bond O, right? So here there is a sigma bond as well as a pi bond. So we know that this is a sp2 hybridized compound And for sp2 hybridized compound, what will be the angle that will be formed in the molecule? For sp2 hybridized compounds, it will have a 120-degree angle since the molecule will be planar in nature, right? So this angle will be 120 degree. So now we are seeing, so they have shown the how bonding is taking place. So we are having an sp2 hybridized carbon atom and an sp2 hybridized oxygen atom that are present. So what will happen? One of the sp2 hybridized orbitals of carbon will overlap with the sp2 hybridized orbital of oxygen, resulting in the formation of this CO sigma bond. So the CO sigma bond is made up of two sp2 orbitals. sp2 hybridized orbital of carbon will overlap with the sp2 hybridized orbital of oxygen, resulting in the formation of CO sigma bond. Okay, and it will be having two more sp2 hybridized orbitals, right? Both carbon as well as oxygen. So remaining two sp2 hybridized orbitals of carbon will overlap with the s orbital of hydrogen, leading to formation of ch sigma bond, as you can see here. The two sp2 hybridized orbitals of carbon will overlap with the s orbital of hydrogen, leading to formation of ch sigma bond. And here, in the case of oxygen, it will be having two lone pairs. So the two remaining sp2 hybridized of orbitals of oxygen will be incorporating that lone pairs. Okay, so this is how the first bonding is taking place. First, the sp2 hybridized orbitals of carbon and oxygen will overlap, leading to formation of co sigma bond. Now we are having a pi bond that is present here, right? So how it is overlapping? So for the pi bonding to happen in formaldehyde, you can see in the case of carbon and oxygen, if we are drawing the molecular orbital picture, the oxygen will be a little stabilized because of the electronegativity. So I will draw it little downwards. So if a pi bonding is taking place, then here this will be the pi bond and this will be the pi star orbital. This will be the pi orbital and this will be the pi star orbital. So the pi orbital will be closer in energy to that of the oxygen and the pi star orbital will be closer in energy to that of the carbon. So because of that reason, you can see here the pi orbital is closer in energy to that of the oxygen. It will have a greater contribution from the oxygen. So that is why here the lobe on oxygen is larger compared to that of the carbon. Okay, so this will undergo overlap, resulting in the formation of the co pi bond. Okay, the co pi bond is made up of the two p orbitals. So apart from the sp2 hybridized orbitals, there will be perpendicular p orbitals present that can undergo overlap, resulting in the formation of the pi bond. Okay, and the empty antibonding orbital will be present. So here, as you have seen, the pi star orbital will be closer in energy to that of the carbon, and because of that it will have a greater contribution of orbital on the carbon atom. So that is why here the lobe is larger in size compared to that on the oxygen. So this is the pi star antibonding orbital, which is empty, and this is the filled pi orbital. So, and we are having this sp2 orbitals forming the sigma bond. So together if we will consider, so this will be the complete diagram of filled orbitals of the CO bond. Okay, so the CO bond, it is formed by um, overlapping of the sp2 hybridized orbitals of carbon and oxygen, and the pi bond will be formed by overlapping of the perpendicular p orbitals of the oxygen and carbon, and there will be empty antibonding pi star orbital that will be present, and its contribution will be larger on the carbon. That is why in the case of carbonyl, the carbon will be more reactive towards the nucleophile because of the presence of this antibonding pi orbital, which is having greater contribution on the carbon atom. Okay, is it clear?
Yes, ma'am.
Okay. Now coming to addition reaction on carbonyl functional group. So we have seen that cyanate Cn minus, which is a nucleophile, it can add on to the carbonyl carbon, resulting in the formation of a product which is tetrahedral. And you can see that here the newly formed center is a chiral center or a stereogenic center. So whichever this center which is leading to the formation of a new chiral center is known as prochiral. Initially it was not a chiral center, but after the addition of the nucleophile, it have resulted in the formation of a new chiral molecule. So this center is known as prochiral center. If we consider the case of acetone, it can also undergo nucleophilic addition resulting to formation of the cyanohydrine. But in the case of acetone, here the two groups that are present on the carbonyl are same. So it is not resulting in the formation of a chiral molecule. So this center is not prochiral. Okay. If the groups that are present on the carbonyl carbon are different and it will lead to formation of a chiral product, then that center is known as prochiral center. If it is not leading to formation of a chiral product, then that center is not prochiral. Okay. Now, if we consider the case of glycine, this is glycine, which is an amino acid, and here two protons are present, which are labeled as green and orange. So, if we replace this green hydrogen with a different group, so that group is given the label G, and it has a higher priority than hydrogen. Okay, so if we for finding if it is R or S, so we can label it according to the priority order. So the first priority will come to NH3 plus, then COO minus, then comes 3, and then least priority for hydrogen. So if we see the rotation, here it is coming in anti-clockwise fashion and the least priority group is away from us. So this new sender is S. So here this green proton can be um, labeled as pro S. Okay, and if we are replacing this orange hydrogen and introducing a new group G, and if we will label the each atoms by priority order, so this is 1, 2, 3, and 4. And since the hydrogen is coming towards us, whatever we will get by rotation, it will be opposite to that of. So since this is in anti-clockwise fashion, it should be ideally S, but the hydrogen is facing towards us. Because of that, it will be R. So the newly generated center will be R. So the orange proton, which is replaced, leading to formation of the new chiral center, is can be labeled as pro R. Okay, and now we will see for a carbonyl group how can we consider the phases. So here the attack can take place from this side as well as this side, right? So if we are considering the attack taking place from this side, that is we are viewing from the left side. So if we are viewing from the left side, the carbonyl can be written like that, and the hydrogen, it will be coming on our left hand side, and the phenyl group is coming on our right hand side. So we can label it like this. Okay, the carbonyl is coming, uh, at the center we will place it, and the hydrogen, it is coming on our left hand side, and the phenyl is coming on our right hand side. So if we label according to priority, the carbonyl oxygen will get priority number 1, phenyl 2, and this will come 3. So the rotation is coming in clockwise fashion. So this phase, uh, from which the attack can take place, can be labeled as rephase. Okay, and if we are considering the attack is taking place from this side, okay, if the attack is taking place from this side, that is we are viewing from this green arrow side, then the hydrogen is coming on our right hand side, the phenyl group is coming on our left hand side, and the carbonyl is placed at the center. So if we number, oxygen will get higher priority, then comes phenyl, and then hydrogen. So if we see the direction of the arrow, it is going in anti-clockwise direction, and so this phase, that is when we are viewing from the green arrow side, that phase is known as psi phase. So this is how we will distinguish between the re phase and the psi phase. Okay, is it clear?
Clear, ma'am.
Okay.
Excuse me, ma'am.
Yes,
Ma'am, can you please explain the last part, the last slide of this previous slide? Yes, ma'am. This one.
this one.
Yes, ma'am.
So we are having a carbonyl carbon, which is a prochiral center. So we have to distinguish between, like if the attack is taking place from the rephase or psi phase. So how can we know which is rephase, which is phase? Sorry, psi phase. So for that, this is our molecule. So we can view it from this side or from this side. Okay. If we are viewing from this orange arrow side, so we are turning in this direction and we are viewing from that side. So the hydrogen is coming on our left hand side, and the phenyl group is coming on our right hand side. So accordingly, we have drawn the molecule here in planar fashion. Okay. The carbonyl carbon is coming at the center, hydrogen is coming on the left hand side, and the phenyl group is coming on the right hand side. And we can label according to priority. This carbonyl oxygen, it will get a priority of 1. Then comes phenyl group and the least priority for hydrogen. And we can see the arrow, it is rotating in a clockwise fashion. So if it is clockwise, then that phase is known as rephase. Okay, the attack will be taking place from rephase then. Clear? And if we are
Yes,
viewing
ma'am.
from this green arrow side, so we will be turning in this direction and we will be viewing. So the hydrogen is coming on our right hand side, and the phenyl group is coming on our left hand side. So likewise we have drawn it in planar fashion, phenyl group on left hand side and hydrogen on right hand side, and we
Yes,
will
ma'am.
number it, and the arrow is coming in anti-clockwise direction. So this phase is known as psi phase. Okay.
Yes, ma'am.
So
Got it.
these are the two different phases from where the nucleophile can come and attack on the carbonyl carbon. Okay. So now, in the last case, we have just considered the carbonyl carbon, and with respect to that, we have described the phases. So these phases are known as enantiotopic phases. So attack from the rephase will result in the enantiomer of the product that is resulted from attack from the psi phase. Okay, so that is why these phases are known as enantiotopic phases. Now if we are having a stereogenic sender adjacent to the carbonyl group, then how the stereochemistry of the product can be determined, so that we will be discussing here. So this model is known as Felkinan model. The most important conformation of a carbonyl compound with a stereogenic sender adjacent to the carbonyl group are those that place the largest group perpendicular to the carbonyl carbon. So we are having this carbonyl group, and adjacent to that there is a stereogenic sender. So this sender is chiral sender, which is adjacent to the carbonyl carbon. So we when we will draw the Newman projection, we will get different conformations, right? So this large group we can place here, and if we are viewing from this direction, the medium group will be coming on our right hand side and small group on our left hand side. And we have to draw the conformation such that the large group will be coming perpendicular to the carbonyl group. Then only we will be getting the most favorable conformation for attack, which is less sterically hindered. And the other conformation will be like this. Okay. So here L is the large group, M is the medium sized group, and S is the small group. So these are the two favorable conformations. Now if we consider, if we give large group as phenyl, medium sized group as methyl, and small group as hydrogen. So here it is drawn like that. Okay. So now what is happening? The nucleophile should come and attack. So the nucleophile will be coming and attack in Bourgade units angle, so that it can overlap with the pi star orbital of the carbon. So better overlap will be taking place when the nucleophile will be coming and attacking at Bourgade units angle, which is around 107 degree. So the nucleophile can come and attack uh, at 107 degree. That is, this arrow shown is with respect to the Bourgade units angle. Okay. So this is the Bourgade units angle. So the nucleophile attack possible from this side, or we are having another conformation. So it is possible like this as well. So four different possible attack of nucleophile is possible according to this uh, like conformation, where the larger group is coming perpendicular to the carbonyl group. So if we consider these brown arrows, where the nucleophile is coming and attacking to the carbonyl, these brown arrows if we are considering, here the nucleophile, if it is coming and attacking at this fashion, it is close to the phenyl group, so steric hindrance will be there. And here as well, it will be close to phenyl group, there will be steric hindrance. And in this case it will be close to methyl group, which is a medium sized group, there also steric hindrance can be there. But when the nucleophile is coming and attacking from this black pathway, so here the hydrogen is present adjacent, and because of that it will be a unhindered approach. So this will be the best approach for the nucleophile, and it will give the major product. Okay. Is it clear?
Yes, ma'am.
Okay. So this is how we have chosen this as the major path that will lead to the major product. Now if we are having an electronegative group, or a living group that is adjacent to the carbonyl carbon. So here you can see that this is the pi star orbital of the CO bond, and this is the sigma star orbital of the CCl bond, which is a living group. So what can happen? These two can overlap, resulting in the formation of a pi star plus sigma star orbital, which will be having energy lower than that of the pi star orbital and the sigma star orbital. Okay. So nucleophile attack can take place at a faster rate here. Okay, because of this overlap of the pi star orbital and the sigma star orbital, the nucleophile is not going and attacking in SN2 fashion. It will attack at this center where the energy will be lower, and it will lead to formation of the product. Okay. So this is the pi star orbital of the CO bond, and this is the sigma star of the CX bond. So ideally, if we are not considering this overlap, then the nucleophile can go and attack on the sigma star orbital of the CCl bond, and the Cl will leave and the nucleophile will be coming there. Substitution reaction will be taking place. But since this are closer in energy, it can undergo an overlap, and it will lead to formation of a new molecular LUMO, which is lower in energy and more reactive. And because of that, the nucleophile can come and attack here, and it will result in the formation of the nucleophilic addition product.
Excuse me, ma'am.
Sure.
Ma'am, unable to understand the arrow represented in the first reaction, kind of, that where the nucleophilic attack is easily found. So once again, can you please
Nucleophile will be
participate?
coming and attacking on the carbonyl carbon center there. Okay.
Yes, ma'am.
Nucleophile will come and attack on the carbonyl carbon.
Okay, ma'am.
See, you can see here the pi star of CO bond and the sigma star of CX bond. If we consider, the pi star of CO bond is higher in energy compared to the sigma star of CX bond. So if we are not considering this overlap into picture, we will be considering like SN2 reaction can take place, leading to replacement of Cl with the nucleophile. But here, why the SN2 attack is not taking place? Because here the pi star of CO bond and the sigma star of CX bond, it can overlap, leading to formation of a new molecular LUMO, which is lower in energy. So here then the nucleophile can come and attack on the carbonyl carbon, and it will result in the formation of the nucleophilic addition product.
Yes, ma'am.
Okay. Now if we consider like Cram's model where chelation can take place. So when the chelation is not possible, so we can draw this conformation. Like the larger group is coming perpendicular to the carbonyl group, so the nucleophile should come and attack here, and it will result in the formation of the product, right? If no chelation is possible, then the nucleophile can come and attack at this position, and it will result in the formation of the product. So this is how we used to draw Felkinen model. But if a chelating metal is present like zinc and all, so in that case, this bond will rotate, and it will come in this fashion such that this sulfur lone pair and this oxygen lone pair can chelate with the zinc metal. So now here the pH will be coming perpendicular to the carbonyl group, and the hydride, it can come and attack in this fashion, leading to formation of the final product. Okay. So if chelation possibility is there, if some chelating metals are present, in that case we have to draw the Felkinen model such that the atoms that can undergo chelation, it will be coming close to each other. Okay.
Ma'am, according to the Felkinen model, when we are placing the heavier group on the perpendicular to the carbonyl,
Yeah.
And then there is another rule means for medium and smaller groups. So on we are seeing the entire group, no, all the atoms, number of atoms, everything, or just the central atom.
I didn't get what you are asking.
Like here I'm asking, we are talking about the entire group, like in
Yeah,
this
yeah.
particular
This one.
phenyl
Mm.
hydrogen and this one
SPH
that,
we are considering.
yes ma'am, phs. So
Mm.
we are taking only s, then from ph we are taking the carbon, or the entire
Entire group we are considering.
okay.
So this is larger group compared to pH. So ideally, according to Felkinen model, this should be placed perpendicular to the carbonyl group
Carbon,
such that
yes.
the least hindered attack will be possible and we will get the product. But if some chelating metals are present in our reaction which can undergo chelation, then here this lone pair on sulfur and this oxygen, it both can undergo chelation with that metal. So this will be the favorable intermediate then. Okay.
Yes ma'am.
So this
Yes ma'am.
lone pair and this lone pair, it will chelate with the metal, and this pH will be coming perpendicular, and the hydrate can come and attack to the carbonyl in this direction, leading to the formation of the product. Okay.
Yes ma'am.
So this, if we redraw in this model, we will be getting this as the final product. So for references for this nucleophilic addition reactions to carbonyl, you can follow this Claydon Organic Chemistry, chapter 6 and 34. Now coming to question number 1. For which of the following equilibrium K equilibrium is less than 1? So here different carbonyl compounds are given and a hydration reaction is taking place here, leading to formation of the hydrate. So in which case the K equilibrium will be less than 1?
Option C.
Option C is the right answer. So what will be the reason?
And presence of electron donating group, reducing the electron philicity there,
Yeah. So as you can
and
see,
hence it will be less reactive for
yeah,
the
this will be
nucleophilic
less
attack.
reactive. So here you can see in this case CH3 is present, which is an electron donating group. So electron donating group. So here as you can see, this will be in this carbonyl carbon will be delta positive and oxygen will be delta negative. So for the reaction to take place, this carbonyl carbon should be more electrophilic, or this electropositive charge this delta positive charge on carbonyl carbon should be more for the forward reaction to take place. But in this case, if an electron donating group is present like CH3, it will donate the electrons by inductive effect, and it will reduce the electrophilicity at this carbon center. So this will be less electrophilic, and because of that the addition of water and leading to formation of the product will be less feasible. But when we consider this CF3, CCl3, etc., these all are electron withdrawing groups. And here you can see fluorine, which is an electronegative atom. So this will also be electron withdrawing group. So this electron withdrawing group, they will withdraw the electron density and make this delta positive charge on carbonyl carbon more. So because of that, these compounds will be more reactive. It can undergo addition at a faster rate and lead to formation of the product. So here the formation of the product is more feasible than that of the starting material. So here the K equilibrium can be greater than 1 in cases of 1, 2 and 4. Okay.
Yes ma'am.
So you can see here when acetone is present, because of the electron donating group, that is CH3. Here the K equilibrium is coming 0.001. And if one of the methyl group is replaced by hydrogen, so the equilibrium constant is increasing. It is becoming 1.06. In the case of formaldehyde, it is increasing to 2280. So, and if electron withdrawing group like CCl3, CF3, etc. are present, you can see the K factor is increasing. K equilibrium is increasing. So we have to consider the structural features. The same structural features that favor or disfavor hydrate formation are important in determining the reactivity of carbonyl compounds with other nucleophile, whether the reactions are reversible or not. Steric hindrance and more alkyl substituents make carbonyl compounds less reactive towards any nucleophile. So this is the factor that is making acetone less reactive, and the reaction K value is coming less than 1. Electron withdrawing groups and small rings make them more reactive. So if the electron withdrawing groups are present, then what will happen? That will push the electron density towards it, pull the electron density towards it, and it makes the carbonyl carbon more electrophilic, and the hydration reaction can take place at a faster rate. Clear, right?
Yes, ma'am.
Okay. So here option C is the right answer. Now coming to question number 2. What is the approximate planar bond angle between the carbonyl CO bond and the bond between carbonyl carbon and the atom attached to it? So if we are considering like this, they are asking what is the bond angle, this bond angle.
120.
120, ma'am.
Yeah, the bond angle will be 120 degrees. So we have seen that here the carbon and oxygen will be sp2 hybridized, and because of that it will have a planar geometry, and the angle present there will be 120 degree. Okay. So sp2 hybridization, geometry, planar, angle will be 120 degree. Clear?
Yes, ma'am.
Okay. So answer will be option C, 120 degree. Now coming to question number 3. What is the correct order of equilibrium enol content of the following compounds? So for determining the equilibrium enol content of the following compounds, you have to consider these factors. One is hyperconjugation, hydrogen bonding, resonance, and other factor is aromaticity, but it is not applicable in this example. So when we are considering hyperconjugation, we should
Alpha hydrogen.
hyperconjugation is affected by the number of alpha hydrogens. So in the case of
6
A,
alpha
what is the
hydrogen.
number of alpha hydrogen?
Ma'am, 6 alpha hydrogen.
Here 6
6,
alpha hydrogen is present. In this case
5,
5,
5 alpha hydrogen. C,
8,
8,
8 alpha hydrogen. And in case of D,
5 alpha hydrogen.
5 alpha hydrogen.
5.
In case of A, here only hyperconjugation is possible. Okay. But in case of B, C, and D, we can see that after enol formation, Here hydrogen bonding is also possible and resonance is also possible, right? So in all these cases, um, hyperconjugation is coming, hydrogen bonding is coming, as well as resonance is coming in case of B, C, and D. In case of A, only hyperconjugation effect is possible. So the least equilibrium enol content will be coming for A. Okay, A will be the least. Now, when we consider B, C, and D, here hyperconjugation is more in case of C.
C, yes, ma'am.
So C will be having the greatest equilibrium enol content. Now in between B and D, which will be having the more equilibrium enol content? Both are having
Option B.
5 alpha hydrogen. B and D are having 5 alpha hydrogen. So which will be having the more equilibrium enol content, B or D?
Ma'am, option B.
In the case of B, here this conjugation is also possible. So here the feasibility of this conjugation will be lesser compared to that in the case of D. Okay, because of the presence of the lone pair on ester, it can undergo this conjugation. So here this conjugation possibility will be lesser compared to that of D. So because of that, this will be the right order. C greater than D, greater than B, greater than A. Okay.
Yes, ma'am.
Okay. So for this enolization to take place, the key factor that we have to consider is the presence of at least one hydrogen atom that is present next to the carbonyl carbon. In summary, any organic compound with an electron withdrawing functional group with at least one pi bond joined to a saturated carbon atom having at least one hydrogen atom may form an enol in neutral or acidic solution, and it can form enolate in basic condition. So for this enol formation, the factors we have to consider is hydrogen bonding, resonance, and hyperconjugation. In two tautomeric form of a compound, hydrogen bonding, resonance, hyperconjugation, etc. have the tendency to stabilize the enolic form. That's why presence of all or one of these factor increases the enol content of the compound or makes the enol form more stable. Okay, so these factors increase the equilibrium enol content of the compound. Hydrogen bonding, resonance, and hyperconjugation. Okay, so the correct answer for equilibrium enol content is C greater than D, greater than B, greater than A. Is it clear? Any doubts?
I'm clear.
Okay. Now going to the next question. The CO bond in carbonyls is polarized, and hence the carbonyl carbon and carbonyl oxygen act as dash and dash respectively. Electrophile, nucleophile, nucleophile, electrophile, Lewis base and Lewis acid, electrophile and Lewis acid.
Ma'am,
So
option A.
carbonyl carbon and carbonyl oxygen. Yeah. So we have seen that this bond will be polarized, and we will be having a partial positive charge on the carbonyl and partial negative charge on the oxygen. Because of the electronegativity of oxygen, it can pull the electron density towards it, and because of that the carbonyl carbon will experience a partial positive charge and the oxygen will have a partial negative charge. So because of this partial positive charge that is present on the carbonyl carbon, it can act as an electrophile, and because of the partial negative charge that is present on the oxygen, it can act as a nucleophile. Okay.
Yes.
Electrophiles will be electron deficient in nature and nucleophiles will be electron rich in nature. Is it okay?
Yes.
Okay. So the
Yes, ma'am.
answer will be option A. Now coming to question number 5. Identify the correct IUPAC name of the following compound.
Ma'am, option number B, 3-methyl cyclopent 2 in 1-one.
Okay. So
Option B.
how we are naming it, numbering it? First, it should be starting from the functional group. So 1, then if alkenes all are there, that will get the other preference. So 2, 3, 4, 5. Okay, so this is a cyclopen cyclopentane ring. Okay, and ketone is present, so on will be coming. In the second position alkene is coming, so 2-ene is coming, and this methyl group is present in the third position. So when we are telling the IUPAC name, we will be giving preference to substituents while writing. Okay, so 3-methyl first it will come, then it is a cyclopentanone. So cyclopent, at the 2 position alkene is the 2-ene, and 1 position this ketone is coming, so 1 on. Okay,
Yes, ma'am.
so the correct answer is option B. So sorry, I forgot to change. Correct answer is option B. Now coming to question number 6. In acetaldehyde, the pi bond of the carbonyl group is formed by the overlap of sp2c sp2o orbitals, sp2c 2pyo orbitals, 2pyc 2pyo orbitals, 3pyc 3pyo orbitals.
Ma'am, option number A.
This sp2 hybridized orbitals of carbon and oxygen that will overlap, leading to formation of the CO sigma bond. Okay,
Okay.
then whatever
Ma'am,
orbit
option.
p orbitals that will be present perpendicular to the sp2 hybridized orbital, that will be overlapping in parallel fashion, leading to formation of the pi bond. So if we are having, see, this is carbon, oxygen, so these are the sp2 hybridized orbitals, so they will overlap, leading to formation of sigma orbital. These are sp2 hybridized orbitals of carbon and oxygen. Bond angle 120 degree. Now orbitals that will be present perpendicular to these sp2 hybridized orbitals. So if we can label like this, they can overlap in parallel fashion, leading to formation of pi bond. So this is 2py of oxygen, 2py of carbon. So the pi bond of the carbonyl group is formed by overlap of 2py of carbon and 2py of oxygen orbitals. Okay. So when pi bond is formed, we have seen that the major contribution will be coming from oxygen and lesser contribution will be coming from carbon. Here will be hydrogen. Or in case of acetaldehyde, one will be with CH3. Okay. So again one sp2 hybridized orbital will be overlapping and this will be hydrogen. Another carbon atom. Okay. So this will be how orbital overlap is taking place in the case of acetaldehyde. Is it clear?
Yes, ma'am.
Okay. So here the right answer will be option C. 2py of carbon and 2py of oxygen will be overlapping, leading to formation of pi bond in the case of carbonyl group. If they are asking how sigma bond of the carbonyl group is formed, then it is by the overlap of sp2 hybridized orbital of carbon and sp2 hybridized orbital of oxygen. Okay.
Yes, ma'am.
So now coming to question number 7. Predict the major product of the following addition reaction using Felkinan model. So this is our carbonyl compound. So it is reacting with methyl lithium in the presence of diethyl ether as a solvent and then quenching the reaction with water. So it will result in the formation of P and Q. So we are asked to find what is the major product, that is P.
Ma'am, option number is
Option number A. Did you try drawing the Felkinan model?
I'm doing.
B will be the right answer. So let us see how the answer is coming. So we have
Ma'am, you have to look at the stereochemistry purpose also, right?
what?
Like how to determine the stereochemistry of this product.
Yeah, yeah.
Yeah, that I have doubt.
So when we are considering this is our starting material. So here we have seen previously the same question while discussing the Felkinan model. So this will be the least hindered path for attack, right? Phenyl group CH3 hydrogen. These are present on the carbon that is adjacent to the carbonyl carbon. So the attack that is more feasible will be from this less hindered path which is adjacent to the hydrogen, and this phenyl group which is the largest group should be coming perpendicular to that of the carbonyl. So two conformations are possible where the phenyl group is coming perpendicular to the carbonyl, and in that the attack of nucleophile from this black flight is more favored because of the less steric hindrance from hydrogen atom. In all other cases, there will be steric hindrance from phenyl here, and in this case, steric hindrance from methyl will be there. So nucleophile can come and attack from this direction, and it will result in the formation of this product. Okay. So in our case, the nucleophile is CH3, right?
CH3.
Okay. So if we will draw OH, H, CH3, and here methyl, phenyl, and hydrogen. Okay, so if we are seeing from this direction, so if we will be looking from upside, the phenyl group will be on our left hand side, and this phenyl group will be on our left hand side, and this CH3 will be on our right hand side. Okay, so that is why it is drawn in this fashion. Phenyl will be on our left hand side, and the CH3 will be on CH3, that is the nucleophile, it is coming on the right hand side. And you can see this methyl group that is present on the carbon where the phenyl group is present is coming towards us, so that is written beta. And this hydroxyl is also coming towards us, so that is also beta. Okay, but in the answer they have just flipped the molecule 180 degree. So here they are flipping it 180 degree such that the CH3 is coming to our left hand side and phenyl is going to right hand side. Just we will flip it 180 degree. So whatever groups that are present above, now it will go below. Okay, so this OH will go below and this methyl group will also go below. Okay, so that
Ma'am,
is why,
because like I can say like ma'am, because they're above the plane, that's the reason why the stereochemistry is same for hydroxy and then methyl group.
yeah, both are coming, like when we are looking from one side, both are
Above the
coming
plane.
towards us now. So that
Yes.
is why both are having the same stereochemistry.
Okay, ma'am. By flipping 180 degree, then the stereochemistry changes.
Yeah, that is why it is coming
Like
alpha.
wedge becomes dash and dash becomes wedge.
Yeah, so option B
Okay.
will be the right answer. Is this clear how it is coming?
Yes, ma'am.
Yes, ma'am. Clear.
Okay, now coming to question number 8. Formation of cyanohydrin from a ketone follows this mechanism. Option A, nucleophilic addition. Option B, electrophilic addition. Option C, nucleophilic substitution. And option D, electrophilic substitution. So the
Option A.
Option A, nucleophilic addition.
nucleophilic addition is the right answer. So we are having a ketone and we are adding sodium cyanide. So it is resulting in the formation of
Cyanohydrin.
cyanohydrin. My internet is okay, na?
Yes, ma'am. It's okay.
Okay. So it is resulting in the formation of cyanohydrin. So what is happening here? We have seen in nucleophilic addition reaction, Cn minus will be the nucleophile. It will come and attack on the carbonyl carbon. This carbon oxygen double bond will break and the electron density will shift towards oxygen, resulting in the formation of this tetrahedral intermediate. Now, this can abstract proton from the medium, leading to formation of cyanohydrin. So here this reaction is an example of nucleophilic addition reaction. The nucleophile, that is Cn minus, is coming and adding to the electrophilic carbon center of carbonyl group. Okay.
Yes, ma'am, got it.
Okay. Now coming to next question. Predict the major product of the following addition reaction using Felkinen model. So here, because this OME is present, we will be drawing like C-plaque model. Okay. So the OME will be coming perpendicular to the carbonyl carbon. So when we will draw, we are looking from this side. The hydrogen will be on our right hand side and methoxy on the left hand side. So if we will draw the conformation where the methoxy is coming perpendicular to the carbonyl, it will be like this. Okay, so this is the most favored conformation where the hydrate attack can take place. Okay, here the nucleophile will be H minus. So H minus, it can come and attack from this direction, leading to,
Primary alcohol.
yeah, OH, OMe, pH, H. So now we will see how it is given in our question. pH and hydrogen are coming in the plane. Okay, pH and hydrogen are coming in the plane. So how we have to look at it? If we will look at it from this direction, okay, if we will look at it from this direction, then pH is coming on our left hand side and hydrogen on right hand side. Sorry, we will look it from this direction. 1 second. Okay, so if we are looking at this direction, The methoxy is coming on our right hand side, and pH is coming above the plane, hydrogen is coming below the plane, and this hydroxyl is coming above the plane, right? OME. Now we have to rotate in such a way that the pH will be coming on the plane. Sorry, opposite arrow. So what will happen? pH is coming here, hydrogen, OH is beta. My pen is having some error. Now methoxy will be coming alpha, and this hydrogen will be coming beta. Okay?
Option B.
Option B will be the right answer. Just they are rotating it, flipping it 180-degree downside, such that the alcohol will be coming, like if we rotate in 180-degree, this hydrogen will go down, this initially above, it will go down, and methoxy will be coming above, and hydrogen will be coming below. Okay?
Excuse me, ma'am.
Yeah.
Ma'am, I have tried making this structure, and my last step is not correct. Where I'm getting, from my side, the mistake is that both OME and OH I have given solid wedge. So, ma'am, means yes, ma'am. From this step, how should we proceed?
Like you have to see from this side. Otherwise, you have to rotate it in such a fashion that the phenyl group and hydrogen will be coming in planar fashion. Like you have to rotate in this direction. Like pH is coming here. So the methoxy will go here. Hydrogen will come here. OH, hydrogen, hydrogen. Okay. If we will draw in this fashion, that is also correct. Before converting it into this dash and wedge format.
Okay, ma'am.
Then if we
Ma'am, one more thing. When the hydrate attack takes place, right, you have shown that hydrate is attacking on the carbonyl, which is next to phenyl ring. Why can it attack through both the hydrogens? Because phenyl is a positive
sorry, I have
right?
Burgade units angle only it will show, while I have drawn it came by mistake.
Okay, ma'am.
Like Burgade units angle, it will come from hydride side only, not from above side. Okay.
Yes, ma'am. Okay, ma'am.
My pen is having some sort of issue. That is why the figures are coming little bold. So you have got it right. How the structure is coming? Option B will be the right answer. So here the methoxy group will be coming perpendicular to the carbonyl group. Accordingly, you have to draw the Newman projection and then the hydrate will be coming and attacking from the less hindered side, and it will result in the formation of this as the final product. Clear?
Yes, ma'am.
Yes, ma'am.
Okay. Now coming to the question number 10. How many tautomers can be drawn for the following ketone?
2.
Is it 2?
Yeah, 2 is the right answer. So what factor we have to take into consideration while counting the number of tautomers?
And presence of that number of alpha hydrogen for hyperconjugation.
Yeah.
Yes, ma'am.
So we have to consider the number of alpha hydrogens. So here in this case, 2 alpha hydrogens are present. Okay. So abstraction of one of this alpha hydrogen will lead to one enol, and the other alpha hydrogen will lead to the other enol. So two possible tautomers are present.
Yes, ma'am. Both. Yeah.
This one as well as sorry.
No, no. No, it should be in all form. Yes.
Yeah. So these two possible tautomers are present for this molecule. Okay. Base can come and abstract the proton, leading to formation of enolate, and it can abstract proton from the medium, leading to formation of enol. So two possibilities are there. So the number of tautomers present are 2. Clear?
Yes, ma'am.
Okay. So answer is 2. Now coming to question number 11. Which of the following has greater enol content than the corresponding keto counterpart? So similar question we have discussed in the beginning. So for knowing which is having the greater enol content, we have to take into consideration the factors like hyperconjugation, hydrogen bonding, resonance, and aromaticity. So in these cases, we can consider this
Options.
hyperconjugation, hydrogen bonding, and resonance. So which will be having the greater enol content among these given examples?
Option C.
Option C is the right
Option
answer.
C.
So here we can consider the number of alpha hydrogens, which is important for knowing the hyperconjugation. So in this first example, number of alpha hydrogens present is
2.
there will be 3, right? These two as well as this one.
Ah, yes, ma'am. 3 alpha hydrogens.
3 alpha hydrogens are present here. In this case, 2 alpha hydrogens will be present. This is an aldehyde. So these 2 alpha hydrogens are present. In this case, how many alpha hydrogens are present?
8.
8 alpha
8.
hydrogens
8
are
alpha
present.
hydrogens.
And in the last case,
2 alpha hydrogens.
2.
2 alpha hydrogens are present. So when we will consider the number of alpha hydrogens present, so this option C is having the greatest number of alpha hydrogens. So it can have more hyperconjugation, and that will lead to more stability of enol form, leading to greater enol content at equilibrium. Okay.
Yes, ma'am.
Yes, ma'am. Got it.
So here the factors we have to consider is resonance, aromaticity, hyperconjugation,
Conjugation.
um,
Conjugation.
like and hydrogen bonding, etc. Polarization, hydrogen bonding. So we are considering just hyperconjugation in this example, that is we are counting the number of alpha hydrogens. When the number of alpha hydrogens is more, then the equilibrium enol content will be more because of greater hyperconjugation. Okay.
Yes, ma'am.
Now coming to the next question. In the reaction CH3CHO plus HCN gives X, a chiral center is introduced. So the product is levorotatory, dextrorotatory, meso compound or racemic mixture.
Ma'am, one more thing before approaching this question, we have to first check whether the configuration is R or S configuration, right?
But in this case, no chiral center is present near to that. No? So attack can take place from rephase or psi-phase.
No,
We
ma'am,
have,
after the reaction is occurred, then only the chiral center will be introduced, right?
yeah,
That's what. So using that, we can determine which configuration is R or S, and according to that, we can determine whether the light will rotate right or left direction.
yeah. So here both are possible, right? The attack can take place from the rephase or it can take place from the psi-phase. Both are of equal probability.
Yes.
So we will be getting equal amount of R and equal amount of S.
Yes, ma'am.
Both enantiomers will be equally probable. So because of that, the answer will be racemic mixture. So CH3 double bond O H. So the Cn minus, it can attack from this side or from this side. Both are equally probable.
Like from above the plane or below the plane as well, right?
Yeah.
Okay, ma'am. Then racemic mixture.
So if we are considering from above the plane also it can attack, from below the plane also it can attack. Both are equally possible. So we will get an equal amount of R and equal amount of S. So because of that, a total if we consider, there will be no optical activity. So that will be a racemic mixture. Clear?
Okay, ma'am. Yes, ma'am.
So answer will be racemic mixture option 4.
Ma'am, one more thing. Because both are present in equal quantities, so there won't be any light rotation, right?
Yeah.
Okay, ma'am.
In case of meso compounds also, there will be two chiral centers present in the molecule, but one will be R, one will be S. So at total if we consider, there will be no optical rotation in case of meso compounds as well.
Yes, ma'am.
Now coming to question number 13. HCN not produce a chiral compound with. So four different ketones are given. So here they are asking, when it is undergoing a nucleophilic addition reaction with HCN, which of the following will not result in the formation of a chiral compound?
Ma'am, option A.
Option A will be the right
Option A.
answer because this is not a prochiral center. Here two groups are identical, so this is not a prochiral center. But when we consider the other examples, see here, these are different groups, these also different groups, these also different groups. So these are prochiral centers. After addition of HCN, it will result in the formation of chiral compounds.
Cyanohydrin.
Hmm.
Okay, ma'am.
So in the case of 1, here since both these R groups are identical, so after addition of HCN, the cyanohydrin that formed will not be chiral because these two groups will be identical. Okay. So we have to see the starting compound is having a prochiral center or not. Accordingly, we have to find the answer. So in this case, option A will be the right answer. Okay.
Yes, ma'am.
Okay. Now coming to question number 14. Arrange them in increasing order according to their reactivity towards HCN. Acetaldehyde is there, acetone is there, di-tert-butyl ketone is there, methyl tert-butyl ketone is there. So we have to arrange it according to their reactivity towards HCN. So this is a nucleophilic addition reaction. So we have to take into consideration the electrophilicity of the carbonyl carbon center. So when the electrophilicity of the carbonyl carbon is more, that time the reaction can take place at a faster rate. If electrophilicity of the carbonyl carbon is less, then the rate will be lesser. Okay. Acetaldehyde, acetone.
Ma'am, can we tell the answer?
Yeah, I will just draw the structures. So maybe
Yes.
you can identify. This is di-tert-butyl ketone, and the fourth one is methyl tert-butyl ketone.
Ma'am, option number 2.
Option number B.
Option number 2.
Option number 2 will be the right answer. So as we have seen in the first or second example, so here electron donating group, when it is present, that electron donating group will decrease the electrophilicity of the carbonyl carbon. Okay. Electron donating groups will decrease the electrophilicity of the carbonyl carbon, and hence it will be less reactive towards this nucleophilic addition reaction. So when we consider methyl group, hydrogen and tertiary butyl substituents, this tertiary butyl is more electron donating in nature compared to the methyl group. So when two such tertiary butyl groups are present, that will be more electron donating in nature according to the inductive effect, plus I effect, and that will decrease the electrophilicity of the carbonyl carbon here. So this will be the least reactive. Di-tert-butyl ketone will be the least reactive. So when one of the tertiary butyl group is replaced by methyl, then compared to tertiary butyl, methyl will be less electron releasing. So because of that, here the rate of methyl tert-butyl ketone will be more compared to the di-tert-butyl ketone. When both of the tertiary butyl groups are replaced by methyl, then here the electron donating nature compared to tertiary butyl will be lesser for methyl group, and hence that electrophilicity decreasing will be lesser. So then comes acetone. Okay, acetone is this dimethyl ketone. Now, in the case of acetaldehyde, the methyl group is replaced by hydrogen. So, the electron donating inductive effect will be lesser in the case of acetaldehyde, and it will be more reactive towards the HCN. So, that is why this order is coming. Okay?
Yes, ma'am, got it.
Okay, fine.
Ma'am, provided one more thing. The carbon should be more electron deficient, right? Carbonyl carbon must be more electron deficient. Then only the attack will be favored.
Yes, yes,
Nucleophilic attack will be favored.
yes.
Okay, ma'am.
The electrophilicity of the carbonyl carbon should be lesser. It should be
Yes, ma'am.
so. it should be more electrophilic. Okay,
Yes, ma'am. More electron
electron
deficient.
density should be lesser there.
Yes, ma'am. Okay.
So here the right answer is option 2. Now coming to question number 15. Which of the following observation does not establish the existence of ketoenol tautomerism in acetone? When treated with DCl in D2O, hexadeuterated acetone is recovered. When treated with D2O bar NaOD, hexadeuterated acetone is recovered. When treated with dilute H2SO4 in H2O labeled with oxygen 18, this compound is obtained, and all of the above. So one of some of these are examples that prove the existence of ketoenol tautomerism. One is not an example that is proving the existence of ketoenol tautomerism. So which one is that? So
Ma'am, is
treat
it option C by chance?
option C is the right answer.
Okay, ma'am.
So in DCl bar D2O, it will result in formation of enol, right? DCl bar D2O is identical to that of HCl bar H2O condition.
Yes, ma'am.
So here, if we are having acetone, sorry, if we are having acetone in DCl bar D2O, what it will happen? It will get deuterated. This oxygen can get deuterated, leading to formation of OD plus,
Hmm.
and then Cl minus, which is present in the medium. It can abstract the proton and lead to formation of enol. Here in case of enol, instead of OH, it is OD, since the medium is deuterated. Now, once this will go to ketone form, so in the media, DCl D2O D3O plus will be present, similar to H3O plus. So it will get deuterated. Okay, so this can take place like other five more hydrogens are present, so it can undergo ketoenol tautomerism, and it will finally lead to formation of hexadeutyrated acetone, right? So this first case established the existence of ketoenol tautomerism. Because of ketoenol tautomerism taking place, that is why we are getting hexadeutyrated acetone in this medium. Okay, in the case of D2O bar NaOD, so this is basic condition. So NaOD, this is similar to H2O bar NaOH condition. So if acetone is present, this OD minus, it can abstract the proton. It can lead to formation of enol. Sorry for this bad drawing. My pen is having some error today. And this O minus can abstract D plus from the medium, from water. Okay, it can abstract D plus from D2O. OD. It can abstract water and it will lead to formation of OD like this. Then as we have seen here, it can undergo ketoenol tautomerism and it will lead to formation of hexadeuterated acetone. So second case also proves the existence of ketoenol tautomerism, right? Is it right?
Yes, ma'am. Right.
Now, if we consider this case in the presence of dilute H2SO4 and this oxygen 18 substituted water, so what will happen? Acetone is present in H2SO4 medium. This will get protonated. So now this water, instead of undergoing ketoenol tautomerism, it can add on to this, leading to formation of hydrate. Okay,
And it will lead to gem diols, right?
yeah, gem
Oh.
diols will be resulted. So OH will be there. OH 18 will be there. Okay, now here it will be OH2 plus. So now if proton transfer can take place, this will be O18H. So whatever initially hydroxyl was present, that will be OH2 plus, and once this lone pair folds, the water will get eliminated, leading to formation of O18 after deprotonation. So this compound is resulted by addition of the H2O18 onto acetone that is protonated. Okay, so it is a nucleophilic addition of water to this acetone, and then removal of water leading to formation of this. So this example is not establishing the existence of ketoenol tautomerism. Okay, here it is talking about nucleophilic addition of water into the carbonyl carbon center of acetone. So these two, DCl D2O and D2O NaOD. So in this condition, when we are treating acetone, it will result in the formation of hexadeuterated acetone. It establishes the existence of ketoenol tautomerism in these cases. But in the case of dilute H2SO4 and H2O18 condition, so we are getting this product that they have stated. So this product, it is resulted from addition of water to the carbonyl carbon instead of this ketoenol tautomerism. So if ketoenol tautomerism is taking place, we will just get acetone back in this case. In this case, if ketoenol tautomerism is taking place, we will just get back acetone. So they have told they are getting this as the product. So here ketoenol tautomerism is not taking place. Instead, addition of water is taking place, leading to formation of this hydrate, which is a gem diol, and then elimination of water, leading to formation of the final product. So option C will be the right answer in this case. It does not establish the existence of ketoenol tautomerism in acetone. Is it clear?
Yes, ma'am, clear.
Yes, ma'am.
So here the answer will be option C. So this was the last question in today's session. Is there any doubt?
Ma'am,
Yeah.
can you please again show the slide where you have shown the reference page, means reference for the
Okay.
week 3?
Okay.
Ma'am, actually, I just checked now. It was mentioned, I think, 34, and when I'm checking with the edition 2 of Claydon, 34th lesson is not the one, it is something else.
Okay. I think my may be then different edition. I will check into which edition I am having and I will tell. Okay.
Okay, ma'am.
So thank you all. If there are no further doubts, we can wind up today's session.
Ma'am, one more thing. Could you please explain that stereochemistry? That what is it called? That stereochemistry you drew, right? That is Newman projection.
Huh. Of which question?
Or that attack of hydride, lithium aluminum hydride in presence of the aldehyde group. That there is some the name, right? That actually I'm unable to.
CPLAC model.
C like yes, ma'am. Yeah.
This.
Felkin and model, yes.
So here we are drawing the OMe group coming perpendicular to the carbonyl. Felkinan only, but since
Yes, ma'am.
this electron donation is possible from OMe, so we will draw the OMe perpendicular to the carbonyl group, and we will be choosing
Yes,
this
ma'am.
pathway for attack of hydride. So we will be getting this as the product by Newman
Yes, ma'am.
projection.
Okay. Yes, ma'am.
Okay. Then if we will draw to this dash wedge form, it will be like this, and we will be bringing the phenyl to planar position. Then we will get this.
Okay, ma'am. Okay, ma'am.
Clear?
But why one more thing? Why are actually rotating phenyl and methoxy and then this hydrogen? That is a rule.
What? Actually,
Like
based on the product that is given in the answer, for getting that, we have just rotated.
okay, ma'am. Okay.
Okay.
Okay,
Otherwise,
ma'am.
for normal subjective exams, you can write this as the product as well.
Okay, ma'am. Fine.
Okay. There are
Ma'am,
no.
this is the
uh,
way how Falcon model progresses, right?
yeah,
Okay, ma'am. Okay.
So, ma'am, the correct option was the one that you told, no? The previous one?
this one.
Okay, this one only. Okay, ma'am.
Yeah. Clear, right?
Yes, ma'am. Clear. Thank you very much.
Okay. Then thank you.
Thank you,
Thank
ma'am.
you,
Thank
ma'am.
you very much.
We can meet next Sunday.
Thank you, ma'am. Good day, ma'am.
Thank
Good day,
you.
ma'am.